That
Yes,
makes
sir.
please don't do that. Rohan or RG, please. That makes it really uncomfortable. Okay, so the first problem is ABC triangle. D E F A B A D E F G, a circle with D on AB and E on AC. No conditions on DE. F and G you get, make circle BDF tangent at F, make circle GEC tangent at G. Let the two tangents intersect at T. Prove that AT is parallel to BC. So how do we proceed for something like this?
We can try to prove that ATF equals TFC.
What equals what?
Angle ATF equals angle TFC.
ATF equal TF. Okay, TF. Okay, sure. But like, do you seem to see a claim here? We already seem to have a claim from the diagram itself. We seem to have that T lies on the circle, right?
Yes.
Yeah.
So how about we go about proving that first? So what is angle TFG? Hello, hello. Hello. Okay, since people are not speaking up, I'll just tell you the proof and I'll move on. So we let the f tangent intersect the circle at some point, let's say t. Then we have the property that angle TFG is equal to angle BDF equal angle this. So hence this cyclicity is done. And so we get the other cyclicity as well. Is that fine with everyone? If not, please respond. It would be better if you speak up because otherwise I'm not really teaching anybody.
It's fine.
All right. Okay, so you know how we can do basic angle chasing. Now that now that everyone is comfortable with that, let's look at another problem from IMO 2019. Okay. I'm looking at problem 1.10. Okay, my bad. It's B centric. Okay, so does everyone know the problem?
Yeah.
Okay, so how do you think we can proceed about this? Anyone anyone who has not seen this problem before? Anyone at all? All of you have done the problem before?
No, I have not done.
Okay. So do you know the question?
Yeah.
Yeah, okay. So A1 is a point on BC, B1 is a point here, PQ is parallel to AB, and P is on AA1, Q is on BB1. We have line P1 point here such that CP1P is angle A, and similarly CQ1A1 is angle B. Prove that PQ, P1, Q1 are cyclic. Do you observe anything in this diagram that seems interesting or seems to be true?
Yeah, tangent at P, circle C P FB.
What? Sorry, you were quite
Circle
not.
CPFB is, I think, tangent at P. The line P1 D1.
Oh, I see what you mean. Yeah.
No,
The
this is
thing
not.
is, it's not even passing through P.
Yeah.
Yeah. Okay, I'll give you a hint. The result that we seem
C
to.
A1 A P1 are concyclic.
What are concyclic? Sorry.
C A1 A and P1.
C A1 A and P1. Yes. Is that true? No. You can look at it by symmetry, no? Like B1 is not on the circle.
Yeah.
Yeah. And we can also vary P.
AP and BQ seem to pass through the intersection of the circles.
Yes. That is in fact true. If we extend line BB1 and let it intersect ABC, E also seems to lie on PQ, P1, Q1, and so does G. Can we try to prove this? Maybe we can
Yeah.
prove that PQ EG is cyclic or PQ EP1 is cyclic. And if we could do all four of these, then we could just be done, no? Can you prove PQ EG is cyclic?
Can you please repeat?
Can you prove that PQ GE is cyclic if G is defined as AA1 intersection ABC and BB1 intersection ABC? Can you prove that PQGE is cyclic? This is basically what's called Reims theorem. Observe that PQ is parallel to AB. So we have that if we add in this point, angle HPQ is angle HAB is angle GAB is equal to angle GEB, which is angle GEQ.
Oh yeah, got it.
So we
Why
get
did we
that.
need H?
Just okay, you can do, because otherwise you can do power of point from here as well. Was what I wanted to say. That you
Yeah,
could
it's
just,
power of point also.
yes,
At H, like power of H is HP into HQ, HP into HA.
HP into HG or
Yeah, HP.
HP into HS into some ratio.
Yeah.
Yes, so that works. So we get that PQEG is cyclic. So if we could just show that P1 lies on the circle with PQE or with PQG, we would be done.
By power of a point, we can do that.
From what point?
From E.
From E.
No,
Okay.
not sorry, B1.
Okay. How do you do that?
So B1B times B1E equals B1A times B1C. Wait a second.
Just reuse Reims theorem. What
Yeah.
you're doing is absolutely right.
What theorem?
Reims theorem, or like the thing we did here. Like we know that B1, P1 E dV is cyclic. Do we? Do we know that?
That's
P1ED.
also
Okay.
Okay. Does everyone see that actually?
Yes.
How?
Oh, sorry. So I would like to continue my pop argument.
Yeah. Okay. Do continue.
So B1B times B1 equals B1A times B1C, which equals B1P1 times B1R.
D. You mean?
So from this, we can conclude that B1PQ is similar to B1R.
Okay. Good. So what he did was, first we'll show that BDEP1 is cyclic. How we do that is EB1 into B1B is B1C into B1A, but B1C into B1A is B1P1 into B1D. So we get that P1EDB is cyclic. And now again by power of point from here, you're just taking a constant ratio of dB. So you get that P1EPQ is also cyclic. Similarly, the other side follows and you get that all of them lie on the same circle.
So, can we just write similarly, or we have to show that also for similarly also?
Similarly is fine. Similarly is fine.
So in these symmetric diagrams, we can just write similarly and we are done.
Yeah.
Okay.
But you must show the first part completely properly, of course.
Yeah.
Yes. So do you see how powerful the simple idea could be? Like we just added a one and like these two good points, and everything just falls apart after that.
Yeah.
Yes.
Can you please state Reims theorem once?
Oh, Reims theorem just says this. It's hardly a theorem. Let's say this was a line, and let's say this is a circle. Now join this, join this. For any point on this line, if you draw parallel line from here, this, then this is also cyclic. It's basically the argument we just did.
Okay. Thanks.
Yeah, that is all there is to Reims theorem, nothing much. Okay, so we are seeing a bunch of simple ideas, right? Like, we did nothing fancy or big brain. We just added sim 2 points, which are okay. I'm not. They seem like it will conquer is the only way I can explain the motivation to add these points.
Yes, but
Yes,
what if
this is,
your diagram is not very accurate?
I think I'm not sure what to say about that. Like with a good enough diagram and like a good enough intuition, you should be able to guess this. But okay,
yeah.
don't be too harsh for not guessing this. Like uh,
I
only
Like
think
one
I'm
or you can.
pretty bad at first.
intersection. Yeah, intersection is in all the diagrams. So maybe intersection can be guessed.
Yes. Also, like the thing is, don't take it too harshly because like only one person on the Indian team which took the exam did add these points and angle chased it. Others had
Oh,
like vastly different solutions.
what was this problem?
I'm a 2019 problem too.
Problem two. Okay.
What did the others do?
Some did moving points, I think.
Oh,
The
What?
I
Moving
like
points?
Pranjal
I,
can explain. He did it right.
yeah. So I think everyone else took P1D FQ1 concyclic. That's a natural claim. It's again Ream's theorem, and then radical axis.
Okay, didn't you do moving points?
Yeah, that end part is moving pointable. You can't directly moving point this.
Right, right. Okay, makes sense. Yeah, so like don't take it too harshly if you were not able to guess it. It's a hard thing to guess in general. So like now that you have seen a flavor of like what basic angle chasing could look like, let us explore the power of point idea because it seems to come up a lot, right? Here as well, right? Hello.
Yeah.
yeah. Okay. Okay.
So there's this thing called the radical axis that a lot of you may know of, and a few may not. So as you know, uh, for like 4 points are concyclic if and only if, let's say, uh, EA into EB equal ED into EC, right? Then only these 4 points are concyclic.
Yeah. Converse. I think this is called.
Yes. So now what we do is we start with a circle and we define its power as this length EA into EB. And as it's same for any point you pick on the A on you pick on the circle, it doesn't matter, right? You fix a
Yeah.
circle.
Yeah.
So we can define power as this way. So there's this notion of radical axis for any two circles. Let's see this circle.
Yeah. Locus of point which have same power.
Yes, exactly. So you can all try to easily show that the locus of this set of points will be a line.
Yeah. When these two circles intersect, this is quite easy. Just the intersection.
Yes. And this line is perpendicular to the line joining the two centers. And this line AC will be perpendicular to the line joining the two centers. And okay, AC will be like perpendicular bisector will be the line joining the two centers. Okay, now that we have this, What happens if I add 3 circles? Any two of them have a radical axis, right?
Yeah.
Let's say this. So this was the radical axis of this circle, and similarly, okay, E is not defined. Okay, let me. What? Sorry, A B equal point C. Yeah. So this is the other circle. Now the radical axis of this is this. So the theorem is that if 3 circles all don't share the same radical axis, then their radical axis concur. Can anyone prove this? Just directly.
It's just perfect.
Okay, just explain it quickly.
Yeah, when the centers are not collinear, then like in this setting, we have circle ABC and ACE and AED. So the radical axis of those two circle is AC, and similar then radical axis of uh, circle BFE and then ACE uh, are given. So let assume that they intersect at H, and then with equality we get that third circle also intersect
Uh,
at H.
okay,
I think
so
I was not clear.
yeah, okay, so let's say the radical of these two circles is AC. Let it intersect BF at H. Now HB into HF is H, like the power of point of H with respect to this circle, but it is also HB into HF is HA into HC by power of point on this circle, which is the power of point on this circle. So the power of point on this circle and this circle is same. Thus H lies on the radical their radical axis as well. Hence EHG are collinear, and we get the theorem. Is this fine?
Yeah.
Okay,
Yeah,
great.
fine, fine.
Now
Yeah.
that we've seen this, let's try an IMO problem. I'll tell you the problem number just a second. Let's look at problem 2.4. ABC is a triangle, and we have the midpoint of each side, and the receiver to equal with receiver to L equal. Now, in this structure, we add in a few points. We take this circle, take this
H
circle.
is the ortho center.
Yes, H is the ortho center.
Yeah, okay.
So we get like these 6 points, right?
Wait, how did they define things?
Okay, I'll tell you the problem again. ABC is a triangle with H as ortho center.
L
M,
and R midpoints.
ML are midpoints. We draw a circle with from M with radius MH. Let it intersect at G and F. Similarly, define DE and JI. Okay. Prove that F, G, I, all these 6 points that we just defined are concyclic.
Oh, can you join AH once?
AH, okay, sure. Yeah.
Zoom in a bit, please. To I
You
think
want to
that
say this is concurrent?
yeah, I think so. Like AH is the radical axis, it seems to be.
Okay, good. How would you prove that?
Uh, just,
KH is clear, I think. But
No, like why does A lie on it?
because
By midpoint,
radical center.
that is parallel, so AH is the radical axis.
Good.
I think A is the radical center of circles.
Uh, okay, repeat that in a second. But like what he said was, if you take this circle and this circle, then as they both concur on H, their radical axis is perpendicular to ln, right? The line joining the centers.
yeah,
But
Yeah,
we
yeah.
know that AH is perpendicular to ln because ln is parallel
yeah,
to BC.
yeah.
So the radical axis passes through A. Okay, good. Sorry, what were you saying now? Uh,
I was saying that the radical axis of these are obvious. The radical axis KH, the radical axis DE and JI are concurrent, but that is clear.
yes, yes. But how can you prove that? Like that, four are cyclic. Can you prove that DEJI is cyclic with what you just said? What you said is perfect, right? AD into AE is equal to AK into AH.
Yeah, yeah. A is the
Then
radical center, or those
this
three
is
circles, so it has same power.
yes. So AJ into AI. So DEJI are cyclic. Great. We got that these four are cyclic, so we'll also get that JIGF are cyclic.
Similarly for B and C, we
Yes,
can.
and GFED are cyclic. But now why all six of these are cyclic? Not just any four of these.
What you said?
Like, but why is this a single circle instead of like three different circles? BEJI, JI, GF, GFED. Why are these not three distinct circles? Why is this one single circle?
Again, radical axis.
Yeah, exactly. Let's pretend there were three different circles for a second. Then what would happen? DEJI and DEFG would have radical axis DE, correct? Similarly, the other two would have radical axis JI and FG. But these three don't concur. DEJI, FG don't concur. Since A, B, C are not collinear, hence we're done. As this disobeys radical axis theorem, all six of these must be cyclic. Is that good?
Like
Yeah.
from what we did from A, that AD into AE is equal to AJ into AI. The same thing we can do from B and C. So that is also, I think, suffices.
No, no, that just gives you that EDJI is cyclic. Then that also gives you EDFG is cyclic.
Yeah.
That
So all
FGIJ is cyclic. But why is this the same circle?
yeah. Okay. Okay. So that you have to prove that they lie on the same circle. Okay. Yeah.
Yeah. So we did radical axis again. We said for the sake of contradiction, assume there are three different circles. Then
Yeah. Okay.
DEFG and DEJI will have radical axis DE.
Yeah. Okay.
Similarly, the other two circles will have radical axis JI and FG.
Yeah, but they are not collinear. So
They're not concurrent, so
yeah,
this is
concurrent.
not possible.
Yeah. Yeah.
And that's the entire problem. That's it. Okay.
Yeah. Yeah.
So yeah, it's a very powerful idea, and we use this oftentimes. This was one particular example that I wanted to show.
Yeah. But sometimes it is quite hard to see this.
Yeah, it's like this idea now that you know, like D E J I. If you prove these four are cyclic, these four are cyclic, these four are cyclic.
No, no. This in this problem, it was not that hard. I mean,
Yeah, I mean it's a P1, so it's not supposed to be that hard either. So as you go to difficult, harder problems, the claims will also become harder, right? Like here, there was just one
yeah,
key step, noticing that A lies on radical axis, then using radical axis theorem. Here, there were just this step was there, right? One observation followed by one nice idea. That's kind of the trope you'll see in most P1s. Okay, now this is like a very famous result that a lot of you would have seen many times. Euler's criterion. You must have heard of it, right?
Yeah.
Well's criterion.
Yeah. So what it
Yeah,
says
I know
is
about that in number theory.
no. the,
Yeah,
the
okay,
the
okay.
the
It's
triangle
not
one.
good.
Uh, sorry. Okay, let me. Okay, why is it not?
That R square minus 2R thing.
Yeah, exactly. We know
Oh,
that.
Euler's theorem. Okay, okay. Yeah,
Uh, oh, I square equal r square minus two r, which is like
yeah,
where one r is
right.
the radius of this and one is in radius. So can anyone prove this? Firstly, we just like rearrange it to a form that we would in fact
Yeah,
correct.
that looks like power of I with respect to the circumcircle of ABC.
Precisely, you're
Yeah,
completely correct.
yeah, yeah. So that means let's join. I mean, we should start like this. Uh, let intersect. Let a point intersect. mm, Let AI intersect at some point. Say let's say what we say. Let's say D.
Okay,
And so now we have to prove that 2R equals IA into ID.
precisely, yes.
Yeah. And so this looks like a cyclic quadrature. So we join DC also, I think.
Uh, DC, okay. What is cyclic? You're saying?
Quadrature AB DC. But what we get from that?
Oh, you mean like this? You're asking to join. Sure, but like, okay, you've reduced it enough, right? You've
Yeah.
already said IA into
Oh,
ID.
now you have to find some similar triangle.
Oh, do you know the proof and you're just trying to recreate it?
No, I don't know the proof. I think.
Oh, okay. Sorry. Go on. So, okay, like you want the quantity 2R. Where is 2R in this circle? Now that you have all this, how do you get 2R?
By applying laws of sign,
No. Just like 2R, where is the 2R if you have to have it in the circle?
diameter.
Perfect. So let's add a diameter, no?
Yeah, yeah.
Okay. Where can we get an R from? Small r.
Smaller. That is in radius. So
Let's just make an in radius. Like, why not?
yeah. Okay.
So we want IF into DE is IA into ID, right?
Yeah.
How can we do this?
I think we have two 90 degrees. I think. AFI a 90 degree and then EAD a 90 degree because EOD is the diameter.
Perfect. We have 90 degrees here and here.
So I
Good.
think triangles must be concurrent then. What I said similar.
AB is not parallel to DE.
Yeah, we have to find another angle which is equal.
Yeah. I mean, AB is not parallel to DE, so that won't work.
Yeah.
Maybe you can find a 90 somewhere else, though, right?
Hmm.
At B.
Perfect. So even EBD is 90.
Now
Oh yeah, yeah.
ABD
AVG also 90.
like so angle BAD equal to angle BED.
BED is BAD. Perfect.
Okay, then it's cyclic.
Good.
Oh, sorry.
Yeah, yeah,
CF.
yeah, it's similar. You're right. This is 90, this is A by 2. So this and this are similar. So what does it become? BD into AI is 2RR, correct? Similarity is this, right? BD,
Yeah,
uh,
but then we have BD equals ID.
perfect. Does everyone know how BD equal ID?
Yeah, fact 5.
Perfect.
Yeah.
Okay, good. So since we have BD equal ID, we have the ID into IA is equal to 2RR, and we're done. Is that okay?
Yeah, quite okay.
Okay, good. Now that we have seen a few different simple ideas. Let's look at something more interesting. How many of you have seen Simpson line?
Yeah, yeah,
Uh, like, how many of you have seen it before or know what it is?
In EGM on chapter 4.
Is that the whole chapter? I don't know. You cannot refer.
It's at the beginning.
yeah.
First
Derive
part is
Simpson line
Simpson line.
bisection and all that.
Okay, okay. So, if you have also seen it, can someone quickly just tell me the proof that like the Simpson line exists, for example?
What we have to prove?
Like if D is on the circle, then these 3 points are collinear, and if D is not, then they're not.
Cyclic quadrators, I think, because they are quite 90 degrees.
Yeah, quickly, just tell the. Okay, anyone just tell the proof?
Yeah. So D, yeah, intersection G. Okay. So D E A G is cyclic, and then
Yes.
Angle DGE equal to angle DAE.
DGE is DAE. Good.
Yeah. So now that angle DAE is an exterior angle in that cyclic quadrilateral ABCD. So
Yes.
that becomes equal to angle ACD.
A. What?
Oh, sorry,
BCD.
BCD. BCD.
BCD. Good.
Yeah, which is equal to angle FCD. Now FCDG is cyclic. So angle DGF is 180 minus that angle. So that is a line 180 minus alpha plus alpha.
Perfect. Perfect. And if this was not the case, we can repeat the argument. DFG is equal to DCA. Like DFG is DCG is equal to DCA. And similarly, DFE is DF DBE equal DBA. So the condition is equivalent to DCA equal DBA, which we know is only if and only if D is on the circle. Awesome. Now that we have this, prove that if D is on the circle and H is the orthocenter of ABC, then DH, the Simpson line bisects DH. Can anyone prove this?
oh, that looks like a parallelogram. I seen a parallelogram also.
Where?
What we have to prove?
Uh,
HD bisects EF, right?
no, no. EF bisects DH.
Oh, okay. We join HF also.
Okay.
Then there is a. This looks like a parallelogram, but
What
not
does?
quite.
No. You're close. What is a parallelogram? What do you think is a parallelogram?
Diagonals bisect in a parallelogram.
Yeah.
Where, yeah,
So just if you have this line, if you have this point, maybe just add a point so that you force a parallelogram. This point, right? If
yeah.
you if you add in the point where
No,
it
no.
intersects AH, then if the problem is true, then IDFH has to be a parallelogram.
IDFH. Yeah. IDFH has to be a parallelogram.
Okay, now that we want to prove that IDFH is a parallelogram, how do you just want IH equal DF, right?
IH equal DF.
That would imply the parallelogram.
Yeah.
Okay, how to do that? Do you know that AH is fixed if as you vary A on the circle?
Yeah.
The length AH is not dependent on the where A is on the circle. It just depends on the circle. So we know that DH prime is equal to AH.
If we reflect H over BC, we would get a what we will get. Uh, if we let the intersection of DF with the circle some point, and then we reflect H, then we will again get a cyclic quadrature. I think that is a lemma.
Uh, you mean H prime reflected over BC is on the on ABC?
Mm, H and the orthocenter of ABC. H reflected over BC.
Yes, that's true. That's correct.
Yeah.
Okay, so what I was saying was, do you know that AH equal DH prime? Like as this D varies, the length DH prime is fixed.
H dash is the ortho center of BBC.
Yes.
Yeah.
Okay. So as we just wanted DF equal HI, we just want H prime F equal AI.
Yeah. So we have to prove
Yeah, cyclic.
parallelogram.
Yeah, but again, what is FH prime? You just mentioned a very nice property, right?
Yeah, it is FJ.
Perfect. So we just want AJ parallel to FI.
Yeah.
Yeah.
But what was angle EFD? Angle EFD equal to DBE equal whatever DA subtends, right? It's DJ. So we're done. DFE is equal to DBE is equal to DBA is equal to DJA.
Yeah.
And that just proves your parallel thing. So that means that Fj equal AI implies Fh prime equal AI implies Fd equal IH, and you get the bisection. Is that fine?
Yes.
Okay, good. Now we come to the actually important fun thing. Steiner line, anti-Steiner points. How many of you have heard of these?
No, I have not heard of
I have.
anti-Steiner.
It's in EGM chapter 10.
Chapter 10. Okay, interesting.
It's
Nickel
not.
points inst. It
It's
is.
not that one. It's a different one.
Oh,
Okay, so if ABC is a triangle and H is the triangle, take any line through H. Okay, Take any line through H. Reflect it over the three sides.
And then the three sides are concurrent on the second circle, right?
Exactly.
Oh,
Boom.
so so what we did is we reflected the line through H over VC.
And AB and AC, and all three
Oh, okay.
lines concur on the circle. Can anyone provide a proof of this?
If we reflect yet again H over BC, then will that lie on the intersection of the line with the circle?
Yes. Like that is just by definition, right? Not by definition, but like that's just the property that we discussed previously. Like
Yeah,
that.
properties that if we reflect H over BC, then it will lie on the circumcircle. But here it is also lying on the intersection of that line from.
I mean, the if the reflection of this line passes through the reflection of H over BC.
Yeah. Okay.
That's just by definition of the line, right?
Yeah. Yeah.
Anybody?
We know that midpoint of EH is supposed to lie on the Simpson line.
Okay, good.
Midpoint of EH.
Yes, we know that by the
Yeah.
lemma we just proved, right?
And Simpson line, what with respect to which triangle?
E with respect to ABC. Let's just see the argument, right? Let's reflect HD over BC, okay? We do not even talk about the other lines right now. Fine? Hello?
Yeah, okay.
Yeah. Yeah.
Okay. Let it pass through E and H prime.
What you reflected? H.
HD, the line
E.
we were
Okay.
given, I reflected it over BC. I let it pass through E. Okay.
Yeah.
Now remember that previously we had in the previous structure. You may remember that the Simpson line was parallel to this, right? That's what we had shown in the end.
Yeah.
What parallel? Which line?
We had proved that the Simpson line was parallel to AG, right?
Yeah, yeah. Okay, okay.
Where E was the foot of perpendicular, like where the perpendicular from E intersected the circle. Okay,
Yeah.
now that AG is parallel to Simpson line, then we also have like EH prime. EH prime is like basically reflection. Like AG must be parallel to DH, correct? Because DH reflected over BC is EH prime, but reflection of AG over BC passes through is parallel to EH prime. Reflection of AG over BC is parallel to EH prime, right? Uh,
Yeah.
Yeah.
I mean, the perpendicular bisector, like BC is perpendicular to both of
This
these.
time it is parallel to DH.
Yes, so like AG is parallel to DH, so the Simpson line is parallel to DH.
Yeah.
But now if we just add in the Simpson line, let's say this, and wherever the
Simpson line doesn't pass through I.
other, Simpson line by definition is through I.
No, I is like reflection of L across BC, not foot of perpendicular. What? No.
I is the foot of perpendicular. No?
No. Oh, never mind. It's not. I think.
Okay, is it not defined correctly?
No.
Ah, right, it isn't. You're right. Okay, let me. Yeah. So
Yeah,
if I
I was not the foot of perpendicular.
yeah, okay, sorry, this one. This is line IJ is a
No, it,
Simpson line, but like we remember that F lies on it, right? Where F is the midpoint
yeah.
of HE. So if
Yeah,
we
we,
take, so if we take ratio 2 of this line from E, then reflection of E over this will E reflection of like J over BC lies on this line because we have proved that JE parallel HK, JI parallel HK, right? Because DH is parallel to AG, which is parallel to Simpson line. The Simpson line and this is parallel, so ratio 2, this just gives that line. If we take
oh,
ratio,
yeah.
yes. So if I take ratio 2 from E, like the feet of reflect E over these sides, it lies on the 3 on the line, right? So if I reflect it back, obviously it passes through E, the line, because this reflection of this point lies, like the reflection of
Yeah.
E across this is on the line. So we're done.
Yeah, similarly for the others.
Yes. Is this fine for everyone? Did everyone follow?
Maybe repeat once again. Like briefly.
Okay. First, we remember that Simpson line is parallel to AG, where G is like perpendicular from E to BC intersect circle. We just proved that in the previous problem, right?
Yeah.
Okay, good. Now that we have that, sorry. Now that we have that, observe that AG is parallel to EH prime. Sorry, reflection of AG over BC is parallel to EH prime because AH,
Reflection of HK over BC is parallel to AG prime.
uh, a reflection of AG over BC is parallel to EH prime.
Yeah, okay. Really?
Okay. I mean they share this their AH prime EG is a isosceles trapezoid with BC perpendicular to it. Since
Okay, okay.
since AH prime perpendicular to G parallel GE. Okay, since that is true, we know that H prime E is just the reflection of uh, BC over like L over BC. So we know that L is parallel to AG. So this line L is parallel to the Simpson line of E. But we remember we just proved that midpoint of HE lies on this line. Midpoint of HE lies on the Simpson line.
Yeah, yeah.
So if we take ratio 2 from E, that sends this line, like that sends F to H.
Yeah, 30.
So it must take this line to L.
Yeah,
Correct? That means the reflection of the feet of altitude from E to the three sides lie on L,
yeah, yeah.
which is basically what we wanted.
Yeah, okay, okay. Got it.
Okay. Did everyone follow? Now?
Yeah.
Okay, great. Now let's look at some interesting problems. Okay, you pick. I have two choices. We can start with the Simpson, a one on Simpson line, or we can look at one which is more interesting and uses this property of Steiner. Problem 3.9 or problem 3.4? Okay, I think you don't have the 3.9 actually.
3.9 is IMO 2011-6 in this.
Yeah, okay, sorry. Not that one. This one, problem 3.4, the unknown source or ISL 2018 G5.
Let's G5 try. Then unknown.
Okay, awesome. Now that's good confidence. I like it.
Oh, this is good.
What?
This is good. Why this is good?
Uh, I don't know. You're just confident that we'll do the
Okay.
G5. It's
Okay.
nice. Okay. Let I equal. Sorry. Okay. What even? Okay. Now L is a random line again, but this time it's even more random. It just does anything. We don't know what it does. It just
Can you
does.
please tell the year of this problem now?
2018.
Yeah, but okay, it doesn't matter, right? For how does it matter for our purposes?
Oh no, so that I can open the question inside. That's why I was saying.
Okay, okay. Yeah, I'll update the file soon on the. I just forgot to do it. So we get these new points. Now what do we do? In the problems tells us, let's draw the perpendicular bisectors of AG, CF, and BH, which sounds ridiculous, but like we kind of have to do it if the problem tells us. And that gives us a triangle. Okay, these three lines will form a triangle. J, K, L. Now we have this magic that happens. J, K, L. Boom. tangent to ABC. That's the problem. So I'll repeat the problem. ABC is a triangle. I is the in center. This random line intersects AI at G, BI at H, and CI at F. We draw the perpendicular bisectors of CF, BH, and AG. We get a triangle JKL. Prove that the circumcircle of JKL is tangent to the circumcircle of ABC.
How can you prove tangent?
What?
How can you prove two circles tangent?
That is the key way you usually do is some sort of homothety that
Oh,
or just angle condition, but more often than not it ends up becoming a homothety.
Because this is in a section about Steiner line and we have a random line.
Okay, so you
So
want to do
maybe M is the Steiner point of something.
great. What? Take a guess. Take a ridiculous guess.
Okay. JK.
Of JK? I, I
Yes.
mean I mean it's not symmetric. If it's of JK, then it's of also of JL and LK.
Oh yeah.
Also, these three lines don't need to pass through orthocenter.
Yeah.
of the line FGH in triangle JKL.
In triangle JKL, why does FGH pass through the orthocenter of this?
Yes.
Okay, that is a good question, but you are right actually. That is in fact true. That if we reflect FGH over this, we get AM, FGH over this, we FGH over what? Yeah, this, we get this, and FGH over this, we get this. That is in fact correct.
I think if someone don't know this standard configuration, then this would have been not possible.
It would have become very hard, but I think
There are other ways to solve it.
but yeah, I think Atul also did it, but and without Steiner line.
Angle chasing.
Yeah,
Angle chasing an alternate way.
yeah. Like okay,
Okay.
Steiner line is much more powerful, and I'll show you a very simple solution. Yeah, like if you know the config, like if you know like what's happening well enough, and if you know what to expect, like I added this problem in today only. So like Atul and others had sent it to me, and because I had seen the idea and I was in the mood of Steiner line because I'd been writing the problem set. I was able to do the problem pretty fast.
Actually, in about like 5-10 minutes.
P6, 5-10 minutes.
G5.
So it's like P5.
That's not relevant, right? Let's more focus on the problem and the config.
Also, if you prove like the M is the Steiner point, then it is already done because there is only one Steiner point, right?
But why does it lie on both circles then? Like I would be fine with it lying on JKL, but why does it lie on ABC? And why do they
Because
intersect only at one point?
Steiner point is one.
Yeah, sure. But like, why is it on ABC?
Yes,
And
so because like from the diagram it is clear that BM, CM, and AM are these reflections, so that's why.
I mean, you need to prove that, no? And
Yeah.
okay, since we want something related to Steiner, and we want to do it on ABC as well, what do you know is a where do you have you do you know a Steiner? Like where is an orthocenter here in this current figure, and of what?
Orthocenter of JKL is supposed to lie on that random line.
You already have the orthocenter in the figure. Where is the orthocenter? I is the orthocenter, right? And if you add in the midpoints of arcs,
Orthocenter of what?
NOP, where NOP are the midpoints of arcs, I is the orthocenter.
Yes.
The only thing we are missing is a line through it. So let's add in a line through it. Let's draw the line parallel to the given line through it. Now I claim M is the Steiner of this line with respect to NOP.
What you just did, can you please repeat?
NOP are midpoints of arcs, like BI
Yeah,
into
that I understood. After that, what you said.
I is the orthocenter of
So
NOP,
that
right?
would be the triangles of the center.
I is the orthocenter of NOP, right?
Yeah,
Yeah.
that I
And
understood.
yeah, so I added the line parallel to the given line through I.
Okay. So what's the use of that?
Yes, I claim M is the Steiner point of this line with respect to NOP
Okay.
because this is the key observation for that. Okay, this is messing with me. Yeah, this is the key observation for that. Do you see the observation? MLP, MKO, and MJN are collinear. So if that were the case, and these two were tangent, then we should be able to scale MJ this like circle onto PON, right? And because M was the Steiner of this line will obviously have to pass through I, and it will become this line in that case. So M would have to be the Steiner of this line as well. That's how I motivated it. Does that make sense?
And you spoke so fast. I couldn't see the points.
Okay, sorry. Uh, we seem to also have that MLP, MJN, and MKO are collinear, right?
Yeah.
So, and these two circles are claimed to be tangent.
Yeah.
So if we do a scaling that takes this circle to this circle, it must take L to P, J to N, K to O, correct?
Yeah.
Yeah.
It must take this line to some line, which
Yes.
passes through the orthocenter of NOP,
Yeah. Yes.
which is this line, right?
Yeah.
And because we were claiming M is the Steiner of this line with respect to JKL, M must also be the Steiner of this line with respect to NOP,
Yes.
anti-Steiner. So let's define M that way. Let's take the line through L parallel to this and define M as the anti-Steiner. Is that okay?
Define M as the. What did you say?
Anti-Steiner of this line with respect to NOP.
What is anti-Steiner?
Oh, it's just this. And the correct term is anti-Steiner point, even though I'm using Steiner.
Okay.
It's the Steiner line and the anti-Steiner point. Line is the Steiner line. Anyhow, we take this now and we get a point M, correct? Is that okay?
Yeah.
Okay, now scale scale this whole triangle, and so that I shifts like so that I shifts to this point. Like that takes this line to this line. Scale from M so that this line goes to this line. Okay. So you have found a new triangle JKL such that reflection of this line over LK passes through M, reflection of this line over JK passes through M, and so on, because of our previous structure. But this you see how why this is already very good if we are getting J dash K dash L dash with these properties. Anyone?
Because then reflections across the sides should meet at M.
Correct. So the thing is, when we were remember we were reflecting this line over the perpendicular bisector of AG, right?
Which one? B. What is this?
We were
PI.
reflecting FH over the perpendicular bisector of AG, right?
Yeah, FH. Yeah.
But if we just move this line like this and just keep it parallel to a fixed thing, it doesn't matter, right? Like the reflection over the perpendicular bisector should remain the same because it will be a same parallel line and it should pass through A, right? Do you get what I mean?
Yeah. Yeah, that's right.
Yes, but remember that PO is like the perpendicular bisector of AI. You know that PO is perpendicular bisector of AI, right? Since PA equal PI and OA equal OI.
Yes.
Yeah, yeah, because of the in-center.
Yes. So basically, this line is always a reflection over LK is AM. So we found reflection over LK is AM, but reflection over the scaled line is also AM.
Yeah,
When
so
we
they
were,
must confirm.
so they must be the same line.
Yeah.
This line is same as the scaled
Yeah,
line.
the
This
two
line is
lines are two lines are the reflections of the same line. So they must be confirmed.
yes. So this line and this line must be the same lines as the one we got from the scalings. So this triangle is the same as the triangle we got from the scalings. And we're done.
This was quite good. I mean this picture. If we draw it on paper, this will.
It was hard.
Yeah.
How can you see like things so quickly in such a complex figure? I mean, it's hard to figure out the points too.
Yeah, it comes with practice, no? Like, and sometimes you'll miss easy things even when you have
Yeah.
practice.
That's right.
Yeah, like yesterday I was trying a problem and I couldn't see a direct parallelogram for half an hour.
Yeah. This problem.
No, some other problem, but
Okay.
I couldn't see a direct parallelogram for half an hour. So these things happen. It's okay.
Now this gives me hope.
Yeah, so don't worry. Like, and it will come with practice. Like, I wouldn't spot this like even say 6 months ago.
And do you recommend using GeoGebra at an early stage?
I would. It would be better if you don't do it. Yeah, if you're stuck, sure. Like if you have no progress but you really want to solve the problem, then sure, just try it for fun. But like if you're seriously problem solving, and if you want to improve your skill, then GGB is probably not the best way.
So it is better to take hints rather than doing
Yeah,
GGB
right.
even after trying.
GGB gives it's spoon feeding, like because GGB gives us quite a lot of facts about the diagram, which we cannot just come up easily on the paper.
Yes, it goes both ways, I guess. Like, okay, if I think like paper has its own advantage. GGB, you said, will give you claims directly, right?
Yeah,
But if
and
you yeah, sorry.
and like in drawing figures, drawing complicated figures on paper is also quite hard. Because in some diagrams we will get the thing which are not actually correct in general, but in GGB we can just rotate or do something else and we come to know easily.
I think it goes both ways. Like, what you're saying is right, absolutely
Yeah.
right. But a lot of the times you don't need an accurate diagram to guess the things. Like, if if you have enough more intuition, or if you know enough things, or if you know how it should be it happening, what should be happening, right? If you have a
Yeah.
good enough intuition about the diagram, then a lot of it becomes easier on freehand even.
Mm.
like, like a lot of the diagrams you end up making, freehand will be good enough. Your claims would be there in the freehand diagram as well.
Oh, freehand.
Freehand,
I mean without compass.
without compass, without scale.
Oh, I have not tried. I don't think at this stage I can. Like in this does require compass and skill. I think this particular diagram.
Sure, I'm not saying that do it immediately. I'm saying that that's also okay. It's not completely ridiculous to do. I'm saying that you don't necessarily need a good diagram. Like, is Pranjal still here?
He left.
Yeah. Okay. For example, he has given me quite a few hard problems. Or like, okay, for example, UCMO 3 this year was a very hard problem.
Which one?
Yeah.
SATS Maths Olympiad, problem 3. But
Yeah, I
like,
think, there was a paper of Anant Mudgal in that
yeah,
thread.
yeah.
That's understandable because I don't know much of projective geometry or inversion.
Yeah. Anant wrote that problem, and like Pranjal was able to solve it much more. Like, he did it on GGB for a lot of time, but wasn't able to do it. But then he said that he switched to paper on a freehand diagram and was able to finish it within 15 minutes with just angle chasing.
What?
Say that's just a degree of comfort you have with each tool, right? Or like,
Yeah.
so
Yeah,
that
that's also a factor.
so it's fine. A lot of things are much easier with GGB. Sometimes you'll just find a few things you can do better on paper with enough practice. Like angle chasing. I I can't angle chase on GGB. I need paper for that.
Yeah, like marking angles. Yeah, right.
Yeah, or just like even writing it down is much more helpful.
Hmm.
I was doing one problem of your handout only, in
Okay,
which that we have to in mode 2020 P5 it was. So in
okay.
that when draw drew the diagram on the paper, it was not even coming complete on a page. So what should we do in that case? Like if we
What
don't use GGB.
what do you mean? Like your
So
diagram was too big, you're saying?
yeah, I even tried drawing very small circles, but in that case also the collinearity was coming out of the page.
Just you'll have, like, okay, sometimes you'll have such ridiculous diagrams that you can't even make a proper diagram on paper,
Yeah,
right?
yeah. You have tried GIMO6?
No, I've not seen GIMO.
Oh,
Yeah, GIMO P6 is not a hard diagram, I'm telling you.
Oh, okay. In some
so
cases, you
so that means I made a mistake for drawing the whole diagram. Are you saying that?
yeah.
Like, why would you look at all three circles? Just pick one and do.
Yeah, I thought that the diagram was maybe symmetric, but I thought if I draw the all full diagram, then I would get something more. But couldn't draw that.
Yeah, so sometimes there's this thing that sometimes you will want to like just ditch certain parts of the diagram. You're like, this seems useless, I can do without it.
Yeah.
And
Okay.
sometimes you can make some part of the diagram like freehand. Like if two lines are like just not concurring, I just make them concur. Like
Like in the case I was saying that concurrency paper can
like if this is like the lines you are making and you're saying like it's concurrency is going out of the paper, right?
yeah.
So what I'll just do is I'll just make it like this and just like this. Okay, these are concurrent in the paper now.
Okay.
Good enough.
Yeah.
Yeah.
Honestly, it just works. It's fine.
Yeah. Also a freehand example also is I guess INMO 2021 P5,
Yes.
because I don't think we can draw it by compass, because there are angles like 75 and 25.
Oh no, it
Yeah,
can be
yeah.
drawn. It can be drawn. I do doing this.
25. How can you draw 25?
Oh, sorry, I used projector. Yeah. Okay.
Yeah,
Protractor is not allowed on INMO?
at
Yeah,
home.
not allowed.
Ah,
Yeah, for practice.
Yeah. So like those cases, you definitely don't need a perfect diagram. Like in book P5, you don't need it to be 25-degree to get what you want.
Yeah.
Okay. So I think we have seen enough ideas right now that we can try some actual problems.
Yes.
yeah.
But this was not an actual problem.
This was just for Steiner instructive purposes, so to say.
Yeah.
Yeah, I wanted
That
to
that
ask
is
like,
also considered.
since we were doing Steiner, so we get the intuition of that anti-Steiner point. But
Yeah.
if we were like seeing the problem randomly, like,
Hmm?
so, I mean, ऐसे क्लास में नहीं कर रहे हैं अलग से कर रहे हैं तो कैसे
Uh-huh.
इंट्यूशन वो प्रैक्टिस
Huh, like here, the problem when I read it, it like just meant it had to be Steiner for me. Like because this line is there and I'm reflecting things across it, and this claim seems to be true. Like after I saw that AM reflected over LK seems to be FH, I was convinced it's Steiner. So it's
Also,
like,
this circle, yeah, this homothety. The homothety is also not very difficult to see.
yes, yeah. So like mostly, yeah. So you noticed right how we prove the tangency homothety.
Yeah.
Homothety is a common idea of proving tangencies.
Yeah.
Okay. Also awesome. Like sometimes you just want to rephrase things. Like we just rebuilt the problem from this like different line, right?
Hmm.
That's something you sometimes want to do, just to make your diagram more convenient or just your things more convenient. Okay. Like sometimes you'll have weird conditions, and you can ask yourself, okay, what property is it asking me to prove? If this is true, then this must have been true. Like okay, sometimes you'll be given some problem. Let's say you're given a problem point x and you have to get to point say z. Okay, yes, you'll be like, okay, if z is true and x is given, then y would have to also be true. Like you don't need to just go from x to y, you can go from z to y as well, right? If this was true,
Yeah.
then y must have been true.
Yeah.
you mean working backwards, right?
Yes, like you can work backwards a lot of times. You'll find your claim, your middle claims from the other side. You can just start z must be true. Okay, so let's make it v. Okay, you have to get from v to z very far. From v you say y must have been true, and from v you say w must have been true. Now you just need one step, right? It's like it's very vague and pretty stupid way to explain, but
A
No,
good
in
answer.
angle chasing we do like this, I think.
yeah,
Okay.
this entire problem was like this, right? You were supposed to get from tangency to tangency, like
Yeah.
from this triangle to this triangle. You're like, okay, this seems true. Some claims will just be like, oh, it seems true, it has to be true. This sometimes your claims will like even if you don't have a diagram. Okay, I'll show you a problem. Let me actually show an example for this.
Yeah. So
Let's try problem 4.18, I think. Yeah, 4.18. Let's try 4.18.
okay.
Uh, has anyone tried the problem before?
I haven't.
Anyone who
No.
has?
Tried and failed.
That's okay.
Which problem?
Yeah, so the problem is you have this and you have this. And okay, maybe not. What was it? Let ABC
Midpoint of AH, not H.
Ah, right. Of course, that makes way more sense. Yes, midpoint of AH. This big circle, right? Now, getting a reasonable diagram of this on paper is just ridiculous.
You can draw arcs, like the required arc only.
Do you even need the circles?
Yeah, the problem is like AO in like this point lies on AO. Okay, like ABC triangle.
So maybe we can prove that O lies on the radical axis of these two centers. Oh no, sorry, it
Like
doesn't. Sorry.
yeah, so like I'll tell the problem. ABC triangle. O line through O parallel to BC intersects at D and E. F is midpoint of H where H is orthocenter. Prove that BEF and CDF intersect on the line AO. When I read the problem, I definitely didn't want to make this point. And like I was doing on paper because I was mocking a test and it was on there. So like this problem reads like you know a lot of things, right? It just seems like something like root BC inversion would work. Like F should be going there or something. Not root BC. If I preserve BE and DC, like if I just change the circles because the power of points from A, then F goes to the other intersection, right?
Can you please take in terms of like simple analysis without if that's possible?
Okay. Let me define some other point like G instead as the point such that AF into AG is AE into AC.
AF into AG equal to AE into AC.
Like AB into AD equal AE into
Yeah,
AC,
that's
right?
right.
Yeah.
So I define G as like AF into AC is AF into AG is also that line, and G is on this line.
What is the even motivation of doing so?
It motivates from inversion ideas.
I mean,
Yeah. So like okay, now what you wanted to was like AFB is like now ACG, right? Sorry, AFE is ACG. Do
similarly,
you, do you see why that is true? A,
E
AFE,
goes to C and F goes to G.
yes, AFE is ACG just because of similarity. You can say
Yeah,
even
yes. Yeah. Homotheity.
spiral similarity from A. Yeah. So AFE is equal to ACG, and similarly AFB is ADG, right?
Yes.
So EFB is basically DGC.
What? EFB, that faint
EFB,
triangle.
EFB, angle
That example
EFB,
is quite faint.
angle EFB is angle D, is angle ADG minus angle ACG, right?
Yeah, yeah,
So that is DGC.
yeah. Similarity by similarity.
Yes. So we wanted just DGC equal DFC is all we want, right? We want to prove these are cyclic. So you just want DFC equal DGC, right?
Yeah.
So we just want EFB equal DFC.
Yes.
Now I can just delete these two circles.
Yeah. So no point of that. Right?
Yeah. So like the whole problem with just this motivation, like that, okay, I don't want to draw that point. Literally, my entire motivation for this was and it reduces to this, equal this. Okay, how do we proceed now? Anything that seems to be true. I'll show you the nice proof. I'll not show you my proof. You can
Angle
go.
CFE 90.
Yes. This is something I did not actually end up noticing. So I did a very long proof. So, and you can check it on the thread, but yes, this is a good claim. CFE is 90, BFD is 90.
How?
That is a claim. It's not,
Okay.
we have not proven it. But if we prove this claim, you see why EFB equals DFC will also follow.
Yeah.
Okay, good. So we can ignore those as well. We just want to prove this 90-90.
So doing one also works, right?
What?
Doing only one also works. Similarly.
Yeah, of course. Just either of them. There's one crucial observation, something you must know. I think you know.
HB is parallel to
H,
FE.
HB is perpendicular to AC and FE is perpendicular to FC, which are not parallel. So that's not true. Also, if that has to be true, since you are taking midpoint of AH, the point such that it becomes parallel to HB would be the midpoint of AB.
Yeah, if that is not true, because then E must be the midpoint.
Maybe think of the B foot.
You want the B foot, okay? Interesting.
Because then this will become cyclic.
What becomes cyclic?
Um, oh no, sorry.
Yeah, it's okay. Don't apologize.
So that is also final EF.
Reflect H across BC.
I'll do that. Okay, like a thing we have used today, like a length condition that we have used today.
How will it help H across BC? Okay.
Sure, I'll reflect H across BC as well.
Maybe if there is a circumcircle, then maybe we can reflect.
Okay,
But
why we can add a circumcircle. Who's stopping this?
yeah, that's for sure.
Yeah. Anyway, the point I was trying to make was that you know that AF equal FH equal OG, right?
Yes.
Do you all know this?
G and D are collinear, I think.
Wait, how?
Oh, this is a well-known fact that OM is equal to half of AH, but you
Yeah.
can prove it.
So
Can
this is
anyone
a
try to
line
prove
point
it?
circle.
I have seen this in many like MH line problems.
Yeah,
People
okay.
using this, but
Yeah,
I
okay.
don't know the proof.
Okay, just can anyone prove it? Can anybody prove it?
With synthetic?
Yeah. I don't want that 2 hour cost thing, please.
I think by homotheity we can prove. Uh, Here we have O is the
Oh,
orthocenter. So
reflect H across M.
yeah, yeah. I was going to say that if we reflect H over M, we get the intersection of line of the diameter and the circle, and then both are midpoints. I mean, O is the midpoint and M is also the midpoint. So take a homotheity at H prime one.
Good. That works. So what he did was we know that a reflection of H across M lies on the circle, correct?
Yes.
Yeah,
So midpoint of like H1 is parallel is equal to HM. So mid what is parallel to HH1? If we take the midpoint of AF and midpoint of AH1, but midpoint of AH1 dash is just O and this is F. So OF is parallel to HM, but we know FH is perpendicular to OM. Thus this follows. Like FH is parallel to OM and FH equal OM. Thus it follows. Sorry, FO parallel HM. So it's a parallelogram. Thus the result follows. Is that okay? Is that okay? Hello.
yeah.
Okay. What I had in mind was slightly different. I can tell that as well. You reflect O across BC. O prime is the center of like O prime is the center of BHC, right?
Yeah.
Yes.
Now we know that the 9 point center of BHC is midpoint of AO prime, correct? Because A is the orthocenter, O is the O prime is,
Yeah,
but
9% is the midpoint of HO.
9 point center of BHC and BAC are the same. 9 points because the 9 point circles are same. So midpoint of HO is also this. So AHO prime O is a parallelogram, and thus the result follows again. Okay. Anyway, we have this property now.
Oh, this was a quite good observation.
Which one?
9 point center observation.
Oh, yeah, it's neat.
It's pretty common, right, when you have H and M.
Yeah, yeah, motivated. That's right.
Yeah. Anyhow, so we have OM equal FH, right? So OM is
Yeah.
also equal to EG. So AFEG is also parallelogram,
Yeah,
but FEGH is also parallelogram.
yes, yes.
So we just want GH is perpendicular to FC.
GH is perpendicular to FC.
See, that's all we want, right?
Yeah.
But isn't that clear because if we extend EG and let intersect FC, then since EF and GH are parallel, so that would also be parallel, so 90 degree.
No, I mean we have not proven this 90. We want to prove it.
Oh yeah, yeah.
So I'm saying if we prove that GH is perpendicular to FC, then we'll also have that EF is perpendicular to FC.
Okay.
Okay. Does anybody spot anything now? Now that I've told you all this.
H is orthocenter of FGC.
H is orthocenter of FGC. Brilliant. How?
Like, I mean, it's supposed to be.
No, you're right. That's it. That just we want that GH is perpendicular to FC, but we know FH is perpendicular to GC, right?
Yeah.
So we just want CH is perpendicular to FG. Correct?
Yes.
What you
But
said? We claim that H is the orthocenter. Yeah, that's
oh,
motivated because we have to show 90 degree.
Oh, but
And
FC
then
parallel to AB.
yes, yeah, I'm getting to it. FH parallel to GC we already have because of definition of H, right?
yeah,
So we just want CH perpendicular to FG.
what CH perpendicular to?
FG is what we
Yeah, yeah,
wanted.
okay, okay.
That would imply orthocenter, so it would imply this
Yeah,
perpendicularity. So if we were just want CH perpendicular FG, but we know CH perpendicular AB, right? So we
Yeah.
just want
yeah, that's it also.
AB parallel FG, but we know AEGF is a parallelogram, so done.
AEGF. Oh, yeah.
So done.
Oh yeah, yeah, done.
This was a P3 on a contest.
Yeah, I guess this is quite a good problem for P3.
I'm not and I'm not too sure about that, but yeah, it was a P3 on a contest, so it's a good problem.
Yeah, this is hard also because
Yes.
there were quite a lot of observations.
Yeah. Okay. I also I did something very different. I had this parallelogram thing though, but after that I did not notice the 90-degree. So when
Can
I
you
tried,
give some idea of your too?
Also,
oh,
EFC H dash cyclic.
what is what is cyclic you're saying?
EFC H dash.
Uh, you're saying F H dash? Yeah. I okay. That's interesting. Let's just do it. So we reflect
So,
E over BC.
so we have to prove EC is the diameter.
So we do this.
Oh,
So we just want E prime HC 90, right?
Hmm.
So we just want E prime H parallel to AB, right? We just want E prime H parallel to AB, but this we have already seen AH E prime E is a parallelogram, so done.
Yeah.
Okay, that's a nice observation. I didn't see that. Cute. Oh, sorry. I did not notice the time. We were supposed to, I think, wrap up 17, 18
yeah,
minutes.
yeah. Battery is also low. So we are going to do more problems or
No. I think we have to wrap up. I did not notice the time. I also have a
yeah,
few
we have
things to
started
do.
a bit early also. 6:20.
Yeah, I also have a few things to do. I did not notice the time. So, yeah, this was. I think we saw a fair number of different ideas and approaches, right?
Yeah.
You can just try the problems now if you're struggling with any, and if you want to really solve it, you can just ping me on the server and I'll try to hint you, or somebody must have tried it and somebody can help you.
Okay.
Can we expect some number theory in the next lecture?